Applies primarily in distributed systems, domain-driven design. Speaking of which, I wanted to ask you, has anyone here read my latest book? Please raise your hands if you did. Okay, quite a few have. You know what? Wait a second. We have to do this all. Your hands? Thank you. Okay, for the rest of you with your both hands down, I have a few copies here. So at the end, if you're going to ask questions, you will have a chance to get one of them. And I know that you have an amazing shop bookstore here in the city. I visited yesterday, I verified they do have some copies, both translated and English versions, so just saying. But today, I'm not going to talk about domain-driven design, but another subject that I'm really, really passionate about. And that's coincidentally the topic of my upcoming book, Balancing Coupling in Software Design. The manuscript is almost ready, it's almost in production. And today I want to give you a preview of this book's material. Now, this is not going to be a sales pitch. My goal is not to intrigue you, not to force you to pre-order it. My goal is to give you some valuable tools that you can use in your day-to-day job, so that you can design modular software systems. Now, I don't know about you, but I've always been told that coupling is bad, that coupling slows us down, cripples our systems, and naturally, when working on a code base that kind of resists changes we want to make, of course, we are blaming it on coupling. As a result, not surprisingly, what do we want to do about coupling? Of course, we want to decouple everything. We want to take all software components and break them into those tiny, tiny boxes. These boxes, they can be classes, serverless functions, microservices, whatever. But the underlying goal is usually the same. We want to be able to evolve each one of these little boxes independently. But what results are we getting by following this somewhat simple reasoning, by focusing only on the size? Well, in many cases, we go from coupled files of code to distributed files of code. In a sense, that's not surprising. As my friend Matthias says, as small as possible is almost universally a bad advice in software design. Or, as Nick Tune puts it, there are many useful and revealing heuristics for defining the boundaries of a service. Size is one of the least useful, and yet we keep on doing that. So I know it may sound controversial, but in this talk, I want to give you a different perspective on coupling, and I will even try to convince you that we can use coupling as a tool for designing modular software systems. So this is going to be our agenda. I'm going to start by defining what coupling is exactly. Then we're going to walk over the different ways coupling manifests itself in software design in different dimensions. And then I will combine these insights into a framework that turns coupling into a design tool. So, what is coupling? If we go to the lexical origins of this word, it takes us all the way back to Latin, where it was composed of two words, co and apere. Co-apere meaning fasten together. In other words, if two things are coupled, it means that they're simply connected. And that makes coupling a ubiquitous phenomenon. It's everywhere. This clicker, for example, is coupled to my computer. Organs in our bodies are coupled together to produce us, to form us, living organisms producing code. Cars, computers, cities, organisms, companies, or for that matter, any kind of system is held together by coupling. You cannot build a system if all of its components are disconnected. This is just a collection of some parts. Yeah, they're organized within the same boundary, but that's not a system. For a system, we need these relationships, these connections between the components. In fact, these interactions between the components, they're making the overarching system greater than the sum of its parts. Therefore, it makes little sense to try to completely decouple everything, because coupling is an inherent part of system design. So instead, let's try to evaluate those intercomponent relationships and see if they're working for us or against us. Let me show you what I mean. Let's say we have these two coupled components here. That downstream on the right references and thus depends on the upstream component. The arrow between them, that relationship, it defines how these components are integrated. It defines how change in the upstream component is likely to break the integration and require cascading changes in other parts of that system. Or as Michael Nygaard says, coupling defines the components' degrees of freedom. How freely the components are able to change without affecting the rest of the system. In other words, the way the components are integrated, it defines what changes can we make in the upstream here without being afraid to break the integration with the downstream components. Now, to evaluate that effect of coupling, we have to understand the dynamics of how coupling works and how it manifests itself. And the interesting thing is, coupling is not some unidimensional phenomenon. It's a bit more complicated. In fact, coupling acts in 3 dimensions. In the dimension of space or distance, time, volatility, and the combination of these two is sort of gravitational force or strength that pulls components together. And with that one, with the strength, I want to start. So the effect of strength is probably the most obvious one. It's sort of gravitational force that pulls components together. It defines what's the impact of a change in one place in the system is going to be on other components in the system. The higher the strength, the more cascading changes are going to follow. Now, let's assume we have these two connected components. It doesn't matter what these components are. I use a pretty abstract term on purpose, component. It's not necessarily a class or a module or a service or a system, doesn't matter. Also, it doesn't matter how these components are integrated, whether it's synchronous communication or asynchronous. It's not interesting. What's interesting for us is what flows across that line between them. What they are exchanging. Any ideas? Information, yeah, that's one thing. We can say that it's data, but yeah, information is a synonym, so we could say that. That's right. But that's not the only thing that the connected components are exchanging. What else? Sorry? Status. Yeah, well, I would categorize it as data or information. What else? Sorry?
Business logic. Business logic.
Business logic. Business logic, yeah, that's true. That's very close to what I wanted to say. Thank you for that. Yeah. So how I prefer to define it is that the components exchange knowledge about each other. Business logic is one aspect of that knowledge. As we're going to see some categories. Business logic is definitely one of them. So when two components are connected, first they have to exchange data or information. For example, commands or queries or results of operations, etc. But they also exchange knowledge about each other. And believe me, it's there on the slide. So the knowledge itself, to evaluate it, as our industry evolved, there were a number of models that were introduced to evaluate the type of knowledge that's being exchanged across couple of components, namely structured design. That methodology was formulated in the late 60s. A model called kinesis. It was formulated in the mid-90s. Now, these two models, they are problematic. First, they reflect different things, different aspects of coupling. So we cannot choose either one of them. We need to use both of them. And second, because structured design was formulated in late 60s, it is based on languages such as Fortran and COBOL. And believe me, this is not something you want to learn, at least not voluntarily. And that's why I decided that given the 30 years difference between these two models, now is the time to start thinking about a new way of evaluating coupling. So what I did is I combined these two models, structured designs, coupling, and connections, into another model. I called it integration strength. I've been using it for some time. I find it really useful. Of course, I want to share it with you because I hope that it will be useful for you as well. Again, basically what it does is it combines the previous model, structured design and connections. It combines and compresses them. Structured design has 6 levels, connections almost twice as much, 11 if I remember correctly. And in structured design, I think, in integration strength, we can do with 4. These 4 levels is basically, they basically give us enough information about the nature of connection between 2 components. So the 4 levels are intrusive, functional, model, and contract coupling. Let's go over them. The first one and the highest one is intrusive coupling. As the name suggests, intrusive coupling is the highest level, and this one shares the most knowledge. It means that the modules are integrated through private interfaces, or they're introducing other dependencies on the implementation details of the upstream module. So let's say you're designing an upstream module, and you have a public interface. And I want to communicate with your module, but instead of using your private interfaces, I'm using other means of communication. For example, I can open your source code and I can look what private fields and methods you have there. And I will use reflection to access or call them. Or maybe you have a database. Again, it's not a public interface, it's an implementation detail. But I decided, no, I will use your database directly. And that's a way of introducing intrusive coupling. Now, needless to say, this integration method is fragile and implicit. The authors of that upstream module may not even be aware of the integration taking place. So any change they are making to the implementation details, it has the potential to break that integration and cause cascading changes in downstream components. In this level, we have to assume as if all knowledge about how the upstream is implemented is shared with downstream components. Next one is functional coupling. And this one means that the connected modules are implementing closely related business functionalities. The practical implication here is that the same business requirements are going to trigger simultaneous changes in both upstream and its downstream components. For example, we can observe a functional coupling in domain-driven design within a subdomain. Now, subdomain is a set of interrelated use cases. What does it mean? Interrelated? Well, usually they are working on the same data, and usually they change together. So that's one case of functional coupling. A more extreme case of functional coupling in domain-driven design is aggregates, because everything within an aggregate's boundary shares the same transactional boundary. all changes should be persistent in the same transaction. So that one screams that whatever you put in an aggregate is functionally coupled. It implements closely related business functionality. An extreme example of functional coupling would be two modules implementing exactly the same business rule or business algorithm, and they have to change together when there is a change to that business rule or algorithm. And the funny thing here is that they don't have to be physically connected, because I can have a system, let's say, with two microservices in it that duplicate the same business logic. And when that logic has to change, they have to change simultaneously, because otherwise the system is going to be in an inconsistent state. So those two microservices don't have to be physically connected to each other, but they are still going to be functionally coupled. A lower level of integration strength is model coupling. This one means that the components are based on the same model of the underlying business domain. And again, we're at a domain-driven design conference, so hey, bounded context, everything within a bounded context is naturally a model coupled. It uses the same model of the business domain. Now, functional coupling, the previous level, it was mainly about the behavior of the system. This one is more about the data structures that are used to describe business entities. Let's say that I'm implementing a component and I have a business entity, let's say customer. It contains data, it contains business logic, but I expose that business entity across my integration interface. Without any translations whatsoever, I just give it out, hey, this is the data of the customer, you take whatever you want from it, use it, I don't care. Well, guess what? The day I will want to change the data structure, I will have to consult my downstream components and ask them, hey, I want to make this change. I want to rename one field, for example. Is it going to break your integration or not? If it's going to break, the integration will be ready because I'm about to change it. So model coupling is more about data structures. It's about sharing the information that you don't necessarily have to share. Sharing extraneous implementation details that you could have keep encapsulated in your module. Now, how can we encapsulate it? Well, that's the lowest level, and that's contract coupling. Here, the components are integrated through an explicit integration-specific model that is decoupled from their implementation model. Going back to the previous example, instead of exposing my customer entity across my API, for example, I could introduce something simple as a DTO. Data transfer object that is being exposed across my boundary, then, well, I want to rename a field, no big drama about it. I rename a field, I just make sure that the translation to DTO is adopted, that's it. My downstream components are not affected by it. And of course, in domain-driven design, again, model coupling happens within a bounded context. Across bounded contexts, domain-driven design prescribes a number of patterns to reduce it to contract coupling. For example, published language in open host service or anti-corruption layer. These patterns, they're introducing sort of a model of a model, an integration-specific model that is decoupled from the model that is used for implementing the business logic, the operational system within a bounded context. So these are the 4 levels of integration strength. They reflect the amount of knowledge that is shared across components boundaries, and it also reflects how implicit or explicit the integration interfaces are. Intrusive coupling, it shares the most knowledge, and it's also the most implicit one and the most fragile one. While if we go all the way down to contract coupling, this one is the most explicit because we have that integration-specific model that focuses on integration, and it's also the most stable one. Now, another way to define the differences between these levels is intrusive coupling would be about the question of how that module is implemented. Functional coupling would be about what functionality that module implements. Model coupling is about the data structures or models being used within it, and contract is about using an integration specific model. Now, let's see an example of integration strength in action. Now, usually we say that, hey, if we have two services, working with another service's database directly is a big no-no. That's not something we want to do. You have to go through a public interface. Let's analyze this example through the lens of integration strength. Now, I'm not going to do this dirty trick of asking you which level it is, because it depends on details, which I'm not sharing here. So now I'm going to share those additional details, and we'll see how the context changes the perspective, changes the integration strength. So first of all, let's say that these two are microservices, and the database is not intended for integration. If component A connects to it, reads data or writes data, God forbid, then of course that's an intrusive coupling. On the other hand, the authors of these two components, they may have decided that, hey, we are working on the same set of data, so we have no choice but to share the database between us. Whether this is a good design decision or bad, it's no longer intrusive coupling. Now we're in the domain of functional coupling because we are implementing closely related business functionalities. On the other hand, let's say that component A is a BI system, business intelligence system, that simply takes all the data from the operational database because they want to analyze it in the future. Well, by doing that, it's no longer a functional coupling. However, they're coupling themselves to the models used in the operational system. And that's why it becomes model coupling. And finally, that database in the component B, it could be an public interface. That database would contain information or data that is there for integration purposes. For example, data mesh approach. It's about using database with integration-specific data and using it for communication. In that case, it's contract coupling. Also, by the way, database doesn't have to be relational or NoSQL. If you look at a distributed queue, for example, AWS SQS, it's not with a database, right? It stores data, it retrieves data. Yeah, its interface is limited, but it's limited because of its functionality, but it's still a database. So in that sense, it still falls here under contract coupling. Now, let's say that we are somewhere around here in the intrusive coupling. Yeah, right there on the first one. Is this necessarily a good design or a bad design? What do you think? Who thinks it's necessarily a bad design? Raise your hands. Good design? No one? Consultants? It depends. Yeah, we have a couple of consultants. Yeah, so that was another dirty trick from my side because we still don't have enough information to decide whether it's good or bad. For that, we need to look into additional dimensions. And the next one is the dimension of space. And turns out the physical location of components in the code base, it also affects their level of coupling. Because the connections between a system's components, they can span different distances. These distances are closely related to what we usually call levels of abstraction. We can have coupling between statements, methods, classes, namespaces, modules, microservices, whole systems, etc. As we go farther to the right side here, the distance between the components becomes greater. Now, the question is, what do we have on this vertical axis here? What is the effect of implementing interrelated functionalities for designing coupling across different distances? What do you think?
Data itself.
Right.
It's gonna be a data itself.
It's going to be
Data.
data. No, it's not going to be about data this time. It's more about the development process. Okay, I'm not going to torture you. So, first of all, it reflects the coordination effort required to implement a change that affects both coupled components. If they're located close to each other, it's going to be way easier to implement that change relatively to if, say, we need to change two microservices simultaneously. It requires more coordination effort in the first case. So we can say that a cost of implementing a change is proportional to the distance between the affected components. And of course, I'm talking about coupled components that are working together. But that's not the only interesting aspect of distance. Another one is lifecycle coupling. In other words, how interrelated are their life cycles? Because here it works in the opposite direction. On the left side, we have interrelated life cycles. If components are located close to each other, well, the chances are we'll have to implement and develop and deploy them together. For example, if we're modifying methods of the same class, well, yeah, it's going to be deployed together. Whereas two microservices, well, the whole idea of microservices is to deploy them independently. So that's the second effect of distance between coupled components. Now, the interesting thing here, distance between components is not only affected by the physical locations of components in a code base. It's also affected by the organizational structure of the company that implements them. Let's see an example. Let's say that we are here on this side, in the microservices, which is on the far right. However, let's analyze two cases. We have to modify two microservices because they are a company. In the first case, the two microservices are implemented by the same team. In the second case, they're implemented by different teams. Well, if they're implemented by the same team, the coordination effort is going to be lower. So the distance between them is lower than in the second case. So again, distance is affected by the location of components in code base, and second, the organizational structure of the company that implements it. And that's a kind of social technical aspect of it. Now, another tricky question, let's say that we have two components, functional coupling between them from strength perspective, that's quite high, almost the highest one. And the components are systems, meaning that the distance between them is huge. Is this necessarily a bad design? Who thinks that yes? Is it a good design? Consultants? Yeah, consultants win. Okay. Yeah, so you've got the point. Okay. To answer this question, we have to ask another one. If a tree falls in a forest and nobody's around to hear it fall, doesn't make a sound. Same here. If two strongly coupled components never change, then who cares about that strength between them if it's never going to manifest itself, right? And that takes us to the third dimension, the dimension of time or volatility. And here the main question is, how often do the coupled components actually change? Now, as the saying goes, predicting future, making predictions is hard, especially about the future. However, we can use some tools that can help us to kind of predict the frequency in which components are going to change. One of them is worldly maps. The second one is domain-driven design. And since we are at a DDD conference, get which model is going to be shown in the next slide. Yeah, it's going to be related to domain-driven designs, subdomains. Now, according to DDD, we have three types of subdomains. And of course, they are different. They have some distinct properties. Core subdomains are all about the company's competitive advantage. These are inventions, optimizations, intellectual properties, or all the things that differentiate the company from its competitors. This is how the company makes or plans to make profits. Generic subdomains, on the other hand, are solved problems. Here we have solved solutions, we have ready-made solutions that we can just use, whether it's an off-the-shelf product or open source, etc. We don't have to implement them. And since that solution is available to everybody, even to my competitors, well, there is no competitive advantage here. And finally, supporting subdomains are somewhere in the middle. Again, no ready-made solution exists, so we have to implement it ourselves. However, they do not provide any competitive advantage. So supporting subdomains, they have to be implemented in-house, but no competitive advantage. And as a result, they will get much less attention from the business compared to core subdomains. And that means that from a volatility perspective, core subdomains are going to change the most. Business is interested in changing them frequently to optimize their business offering, to increase their competitive advantage, and ultimately to increase the company's profits. So when evaluating the effects of coupling in a software system, it's important to also analyze the subdomains at play and how they are going to affect the volatility rates of the coupled components. And overall, these are the three dimensions that describe the nature of coupling between two or more connected components. Now, the interesting thing happens when we will try to combine them together. So, let's see. First, strength and volatility. The higher the strength, the higher the probability of cascading changes. The higher the volatility, the more often we will have to take care of those cascading changes. Sorry. So when both are high, we get high maintenance effort of the relationship. Strength and distance. Distancing the components physically increases the coordination effort required to implement the cascading change. High integration strength over high distance makes the system very expensive to change and maintain over time. Again, because of high distance, we have high cost of changes. Because of high strength, we have high frequency of such cascading changes. And the distance and volatility dimensions, they reflect the coordination effort that is needed to evolve the system over time. If both are high, expect communication overload, frequent communications between distant teams, different parts of the organization. But that's still not the complete picture. To get the whole picture, we need to combine the three dimensions together. And combining them together allows us to estimate the pain we'll have to endure by maintaining that relationship. Now, that pain can be evaluated simply by multiplying the three values. It's integration strength times volatility times distance. Now, if all three are high, well, the pain is going to be high, right? Now, if you want to minimize the pain, make it zero, what should we do?
If it one has zero.
Yes. Yes, one of them has to be zero. That's it. Let's see the three examples. if we can reduce integration strength to minimum contract coupling, for example, then it's okay to have high volatility over high distance. Yeah, cascading changes will require lots of collaboration efforts, but that minimal strength, it minimizes the number of such cascading changes happening in the future. If both integration strength and volatility are high, then we can reduce the distance. And in this case, let's say that the integration strength is high for a reason. You cannot reduce it. For example, let's say you have a components or modules that are implementing closely related business functionalities. There is nothing you can do about it. Either you need a functional coupling there or model coupling. So again, what you can do is reduce the distance, bring them closer to each other. Yeah, it will cascade. The changes are going to be frequent, both because of integration strength and high volatility, but because the distance is minimized, implementing them will require much less coordination effort because it's as if you're modifying one component, they're close to each other. And finally, if the volatility is zero, then yeah, high strength over high distance won't really affect you. That's why, for example, it's okay to have intrusive coupling to fetch data from a legacy system. Yeah, you're working with an implementation detail of that legacy system. You're getting the data from the database directly. It's an implementation detail, and if it changes, there will be problems in your future. But if that system is defined as legacy, it's not going to change. So the volatility is zero. As a result, the pain is zero as well. Now, I call it pain because it's vivid and somewhat funny, but other more serious people than I am, they call it the cost of coupling. So that's another way to call it. We can use that term as well, cost of coupling over time. So to sum it up, the algorithm is the following. First, you want to minimize the integration strength. You have to avoid accidental couplings. For example, if you have a functional coupling and you can reduce it to a model or contract, do it. Or model, reduce the contract if you can. If you can't, if you need to use the same model, then yeah, well, life is tough, you have to keep it there. Don't try to achieve the minimum level at all cases. Sometimes you need higher levels of integration strength. So reduce it as much as possible and adapt the distance. If you end up with high volatility and high strength, reduce the distance. If you end up with a high volatility and low distance, then you can increase the distance. Now, let's see another example, and kind of example I started with. And that's pretty common for this example with piles of code. It's pretty common for companies that are decomposing their monoliths to microservices. And I've heard the story many, many times about a CEO or CTO reading a book about microservices, thinking that, hey, this thing is going to solve all of our problems, so that's what we're going to do. And then they're trying this approach. And of course, they're doing a little POC because they have to be reasonable. They're not going to do it for all the code base. They will start a little POC, and it works. It works flawlessly. So they say, okay, let's continue. Let's decompose all of our code base because that stuff works. And then they fail more than miserably. Why the hell? Well, usually because when they're doing that POC, they're doing it on some non-business critical component, or in other words, on support subdomain, or in other words, low volatility. When they proceed with the same decomposition strategy, for example, let's say something really smart like limiting microservices to a number of lines of code, Please don't ever do it. And they apply it to core subdomains. Suddenly they find themselves in a world of pain. Why that happens? Well, because integration strength and distance and volume, all of them are high and the pain is high. Another example is, of course, domain-driven design. And I mentioned it a couple of times already, but if you look at domain-driven design's patterns, you will see these underlying principles apply there. For example, aggregates. In aggregate, we have very strong functional coupling. So high integration strength. Usually we implement aggregates in core subdomains, so volatility is high as well. What do we do about it? We reduce the distance, we minimize it. We put everything in the same aggregate. We usually say that supporting subdomains can be implemented with some rapid application development. That you don't need event sourcing or domain model, aggregates, value objects, etc. for supporting subdomain. Keep those more advanced tools and techniques for where you really need that core subdomain. It's not support. Why is that? Well, because supporting subdomains are not going to change frequently. In other words, volatility is low. That's why it's okay when designing supporting subdomains to introduce high strength over high distance. And finally, we have a couple of patterns in domain-driven design that help us to reduce integration strength to contract to the minimal level. So anti-corruption layer, open host service, published language. These patterns, basically what they're doing is they're intended for integration across bounded contexts, which means high distance, and it assumes high volatility. That's why we reduce strength to minimum to contract. Okay, I'm almost on time, so quick wrap up. Coupling, it's an inherent part of system design. You cannot design a system without coupling. And it happens in 3 dimensions. The first one is integration strength. It reflects how much knowledge you are sharing between the components, prototypes, intrusive functional model and contract. Next, we have distance. It also affects the coupling, how components are located physically in the code base. Volatility, how often do the coupled components actually change? Different ways to estimate volatility. I love domain-driven design. There are other ways to do it, like Worley maps. And finally, we can combine them together to evaluate pain or cost of coupling in a system. Now, in this book that hopefully will be published pretty soon, I'm describing the relationship between integration strength model and kinesis and structured design. How that model came into being, and also that pain function, it's elaborated a bit more to reflect also the system's complexity. For that, I'll need another few hours, but I'll tell you just one thing. Make sure that either strength or distance are 0. If both of them are going to be 0, it's not good. And just remember that. And with that, reminding you about your awesome bookstore, and we have 2 minutes for questions. So if you have any questions, you have a chance to get one of these books.
大家可以踊跃提问，就是现场你可以有方案。
I'm just wondering, in practice, is it possible to, like the function, pin function, is it possible to alter the whole fundamental design of the strategy?
Of code base?
Yeah, like for example, in the beginning, you think the strength is low, and possibly doing the development of the code base, then you find out the strength is actually high, and that fundamentally changed the whole strategy of how you tackle the design itself.
Wow, that's an amazing question. Yeah. So yeah, I use that method in modernizing a couple of systems. And the interesting thing here is what you are getting when you are analyzing a relationship between components, not necessarily what's going to be there in a month or 2 months. There are different aspects that affect the design of a system. So things change over time, and each one of these dimensions can change as well. So yeah, great question. It can be used to modernize the system, but it's not something that you do today and you forget about it. That's like an architecture, it's continuous effort. You have to keep an eye on those relationships and you get a book. And in the meantime, next question, please.
Thank you.
Yeah.
I'm curious about how much time should I spend when I analyze any development or drug analyze to architecture.
How much time you should spend on it?
Yes.
Yeah. Okay, so the question is how much time I should spend on analyzing architecture. Well, my approach is I always keep this in the back of my mind when I'm working on code base. So I'm looking at the code and running in my mind what kind of integration strength do we have here, what's the distance, and what's the vulnerability. It's not something that requires to do in a workshop like event storming or border mapping. It's something you can do as you are developing your code. So, and it's simultaneously not a lot of time and a lot of time. So you can keep it in the back of your head when you're working on the code base and apply it. You get a book. Next one.
You got two more.
Two more.
Setting a boundary, how can I define the domain and tackle with other teams and let them know why we specific this domain to this team, not be this problem?
Yeah, so when I define a domain, how I can communicate to other team, the reason behind the boundary, right? That was the question. Yeah, so you can use the integration strength to help you with that. If you can define your domain in such a way that reduces the integration strength with other domains, with other bounded contexts, then it's a great justification to put a boundary between them. For example, if you can implement concept coupling between them, that's great. That's a great heuristic that you can put a boundary there. If on the other hand, you see that, well, I need to use the same model. So you're in model coupling, you're probably in the same bounded context. If it's functional or graphic intrusive, that's another case. So yeah, I would say you can use these 4 levels of types of knowledge that are shared across the boundaries to design a boundary and to use it for explaining why the boundary is there. Okay, come later to get a coffee.
Okay, this will be enough.
Yeah, another question. We're out of time, I think, but
Talking personally, what are some of the games that you went through and like have you seen in the history that inspired you to find something?
oh, thank you so much for this question. Yeah, so what was my inspiration? So I did a microservices project and failed in every possible way. And I said, okay, I have to understand what's going on there, why it turned out so bad. So I decided I want to learn everything that is out there about the coupling. And that's how I discovered structure, design, connections. I tried to apply it, didn't work. I ended up formulating integration strength to make it more accessible to people in the team. And then I did that stupid thing of signing contract for writing a book. So thank you for the question. The book is here, it's for you.
It's almost time's up, but can maybe ask the audience to get up with Stu outside.
Yeah, let's do it. So we have one other book afterwards, and if you have questions.
好，那我们早上的听众时间都到中，您先休息一下，待会大家再按这个疫情时间表再换进来，谢谢大家。